0.100 or 0.101 and show them here as blue and red. The interesting behavior is that two of them follow each other quite closely initially, the first 5 iterations or so. And then at some point, the two trajectories of the two iterated series then start to diverge. Now, they diverge to a certain point because this is a quantity which has a limited dynamic range, so it can't diverge to infinity. So, but within that limited range, these two iterated maps now have pretty much uncorrelated behavior. So this is an example of the extreme sensitivity to initial conditions, which leads to a lot of interesting issues, including the difficulty in making a long-term prediction and the sensitivity of this kind of iterated map to any kind of noise that gets injected into the map. So these are some of the characteristics of classically chaotic systems, which are realized, of course, in many phenomena, including the weather. The weather is our ability to predict the weather is ultimately limited by the deterministic equations which suffer from imperfectly defined initial conditions. So we can carry this now into the mechanics realm and think about an iterated map which involves a particle trajectory. So now we're getting a little bit closer to physics rather than simple 1D maps. So now here's a region of space, a rectangular region of space which bounds a point-like particle which has a well-defined position and momentum. So these are point-like mathematical entities. We can imagine launching these things with initial position and initial momentum, and then follow the iterated map which is involved in the collisions of this object with the perimeter of the billiard. It's another kind of iterated map, two-dimensional map. And if we took a slightly different initial condition, we would get another trajectory that would be roughly following the initial trajectory in this particular kind of an integrable billiard. This should be contrasted with what happens in a non-integral billiard, the Swinomivic billiard, which is concentrated on the inner white line here. And in this case, we're showing the same phenomenon, which is to start with two slightly different initial conditions, and follow this iterated map, which really now is a trajectory that bounces off the walls of the billiard. And we see that these two trajectories then pretty quickly start to diverge from each other. And after about the 5th iteration or so, these particles are now moving off in very different directions. So that's a manifestation of classical chaos now in the context of billiards. This is done in Hamiltonian mechanics. It's energy conserving elastic collisions. And so one way to parameterize what's going on here is to think about the difference in initial conditions and then applying the Hamiltonian map essentially as it bounds around inside the bounded region. And then we see that the positions, either coordinate space or in phase space, start to diverge. They increase in time or iteration number in a manner which is exponentially growing with the iteration number of the time. This exponent is positive. This is a sign, this is called the Albanov exponent. It's a sign that there's underlying chaotic dynamics. So this is just a quick review of classical mechanics, chaos in classical mechanics, where everything is very clearly defined and well established. So now the question is, what happens if we now launch waves into the same kind of a bounded region of space, into a billiard type geometry? So the first problem is, of course, that waves don't have trajectories, so we can't perform that little picture that I showed you earlier. If we have two different initial conditions for the waves, they simply diverge from two different points, and there's no trajectory associated with their motion. And so I can't even talk about this concept of diverging trajectories. Right? So clearly, this is not a concept that's useful at all for wave dynamics. So again, second thing is that we're also going to be considering linear wave equations with linear potentials. So the Maxwell's equations and the Schrodinger equation, which I illustrated earlier as being two kinds of descriptions of wave phenomena, will be used to study these chaotic systems. But these are linear wave equations, so we don't have any hidden nonlinearities that are going to give us chaos in space either. So these are two strikes against the whole idea of wave chaos. And really, strictly speaking, it just doesn't exist. It's just not a correct concept. Yeah. Yeah. So we're expecting on the map. So if it comes to the iterated map, we have described collisions of the wall. So if you look at the x and the p associated with the location on the perimeter of the billiard and
But still, the initial conditions might be slightly off, right?
But I have nothing to follow. I don't know what quantity to calculate. And I can work in phase space. I can work in terms of a density function in phase space. But diverge because of the reflections off the walls, but then they would also diffract. Yeah. Well, so what I will do is take the first step, think about what happens in the limit in what we will semi-classical. But they're still there. So what I really need to do is work in a regime where I get both of those. So I need the ray trajectories in the semi-classical limit, but I also need some diffraction. I want to get interesting wave phenomena at the same time. And so wave chaos is kind of a compromise between those two ideas. So you're thinking about solutions to linear wave equations. You're in the semi-classical limit, and you're trying to retain some of the wave properties, but also realize or recognize that there is a wavelength going to zero limit, which does recover classical chaos. That's the whole idea of these kinds of systems. So work inside chaotic billiards, but work in the wave regime, semi-classical regime. So this just illustrates that idea. So again, if we think about a billiard, this is the Kunamovich billiard. These are low-order quantum or wave-like solutions to eigenmodes of the system. This is a very high energy, very short wavelength solution, which of course is just the chaotic ray trajectory. And so what I'm really interested in is this intermediate regime, the so-called gray area here between the classical array limit and the wave or quantum limit, where I have features from both, right? I can see the finite wavelength involved in these eigenfunctions, but I can also see lots of trajectories in there as well as underlying stars, trajectories within the system. So I'm having a little bit of both, essentially. So this is really the regime that I'm going to be talking about. Not the quantum regime, not the classical regime.
So have you discussed or any kind of
they're in there. They're lurking in there. Right? So there's ways of trying to pick out periodic orbits that might exist inside a billiard like this by looking at projection of that against a certain scarred wave function. But as you go up in wave number, go up in eigen number, the density of scarred nodes becomes fairly low. So the first approximation is more depending on what you're doing. So. Okay, so the question is, how common is this phenomenon of wave chaos? So my objective here is to convince you that it's everywhere, it's found all the time. These are three classic billiard shapes, the Sidai billiard, the Kunamovich. This is our favorite, which is the bow tie, which is made up of 4 intersecting circles, convex billiard. And we're looking at this in the semi-classical regime. I'll just leave it. I won't say too much more about this, but in nuclear physics, in mesoscopic physics for electron transport, in acoustics, vibroacoustic of irregular blocks, vibroacoustics of car frames, for example, room acoustics, electromagnetic waves and enclosures, and other examples as well, are all situations where we are in this regime of wave chaos, where these ideas are important. And the basic idea is the following, that if you were to imagine going to the classical limit and recovering chaos, does that actually have any effects on the wave properties? The answer is yes. So it's somewhat surprising that a wave system knows or is somehow aware of the fact that in the semi-classical limit, in the short wave-like limit, when you recover chaos, that has measurable and qualitatively important effects on the wave properties. So that's really what I'm going to talk about now is what are those effects? How do you see the effects of classical chaos in the semi-classical regime? All right, so I'll very quickly just talk now about the theory behind this and then move into the experiment, which is really where my strengths are. Okay, so the theory is the following. This goes back to Eugene Wigner and his attack on the problem of how to understand the energy levels of complex nuclei. So heavy nuclei, what determines the energy levels eigenvalues, the eigenenergies of very complex systems. So lead nucleus, for example, large numbers of neutrons and protons, which of course are really quarks and gluons, and very complex physics. It's very difficult to even write down the Hamiltonian that describes such a system, let alone solve this Schrodinger equation for the eigenvalues and eigenfunctions. So his first approach was to simply say, let's give up on trying to find the real Hamiltonian. Let's populate a hypothetical Hamiltonian matrix with Gaussian random variables in the matrix elements, and then examine not the eigenvalues or eigenfunctions themselves, but the statistical properties of the resulting solutions to the Schrodinger equation. All right, so this is a complete throw your hands up in the air approach and just see what happens when you do this. What he discovered is that by looking at the statistics of the nearest neighbor spacings of the eigenenergies and some of the scattering properties of nuclei where he was sensitive to the eigenfunctions, he was able to get very good agreement between the predictions of random matrix theory and real data. So what he noted was that this is a very simple model. You've thrown out all of the details of the physics, and what counts now are only very, very general symmetries of the system, which is whether or not the Hamiltonian you're working with is orthogonal, unitary, or from the symplectic ensemble, which means that you either have real matrix elements where there's an individual single Gaussian random variable, unitary systems which have two independently fluctuating Gaussian random variables, the real and imaginary part, or if you have a spin a half degree of freedom, then you can have a symplectic matrix element will have four independently fluctuating degrees of freedom. So those are really the only three main universality classes that you have to consider in most of physics. The next step occurred in the 1980s, where it was recognized or hypothesized that any kind of a complex wave or quantum system which has chaotic classical dynamics in the classical limit, their counterparts, their wave or quantum counterparts, possess universal statistical properties described by random matrix theory, which is what I just described here, introduced by Victor. So this is the basic idea. It's called the BGS conjecture. Bohegas, Giannini, and Schmidt, and they put this out, and essentially people have been examining this conjecture for many years since then, and it's been verified to lesser or greater extent in many different kinds of physical phenomena, including the properties of complex nuclei, complex atoms, molecules, transport through quantum dots, lots of work in acoustics, even seismic acoustics, optical resonators, random lasers, and electromagnetic systems, as I'll show you in my work. And so this is something that's been investigated quite a bit. And the kind of questions I've been looking at over the past 15 or 20 years are things like this, which is, are there other kinds of data? Are there other kinds of systems which fall into this class of universal statistical properties that haven't been recognized before? Are there any new applications that are enabled by recognizing the existence of wave chaos and using the BGS conjecture to make something interesting happen, something useful happen? The other question is, if we look at subunitary systems, so these are all unitary evolution systems, if we include loss, or if we look at a quantum system which is coupled to an outside bath and decohering, can you still make predictions based on random matrix theory for such systems? And finally, what causes deviations from these random matrix theory predictions? So it turns out these are universal predictions, but there are lots of exceptions that are seen. The question is, why are there exceptions? What creates an exceptional behavior? So this is a list of all the things I've been working on. I'm not going to go through all of that stuff. It would just take too long and be very boring. So I just want to hit a few highlights of things that we've done in the context of experiments. Right, so I want to show you how we've addressed these kind of interesting theoretical questions through direct experimental work. So that's really the remainder of the talk. So let me just introduce you to our experiment, the microwave billiard experiment, and then just talk about a few results that we've gotten. Hopefully convince you that this is an interesting way to think about things. Complex systems. So what we work with is a quasi two-dimensional microwave resonator. So it's a very thin metal box. It's empty on the inside, and it supports a very simple kind of electromagnetic wave. Instead of a full 6 degree of freedom electromagnetic wave, it just supports one component of electric field and two components of magnetic field that propagate inside this empty box. This is convenient for making a comparison between the results of our electromagnetic experiments, which obey the Helmholtz equation for the electric field in the z direction, with the boundary conditions of the electric field goes to 0. This is directly directly analogous to looking at a Schrödinger quantum well problem, which is defined by the same boundaries of the billiard. It's a flat potential, so it's an infinite square well potential, where the wave function goes to zero. The boundary is an analogy. So it's a direct analogy then between the time-independent Schrödinger equation and the Helmholtz equation in that case. So that's kind of a nice thing. It's not necessary, but it's kind of fun to point this out. And this was originally done by Hunter and Stockman in Germany. And the billiard that we look at, yeah.
How much is it?
Well, H bar is whatever you need. So H bar is the quantity that you tune to give you either the quantum behavior, if H bar is big, or the classical behavior to make H bar go to zero. So H bar for us is sort of related to the wavelength, the wave number. Yeah. So we can tune it to be anything we want. So we don't need that. Having it a constant is really very convenient. Yeah. We just make it what we need it to be. Yeah. So the billiard we look at is this bow tie billiard, which I mentioned earlier, which is the intersection of four circles. And then we symmetry reduce it by cutting it in half and cutting it in half again. So we just look at what we call a quarter bow tie, which is here. So that's a microwave billiard with a slab of brass in which we milled out a section in this shape, about 8 millimeters deep, and we allow microwaves to propagate around inside the box. Okay? And the solutions to the Helmholtz equation can then be mapped directly onto the solutions of Schrödinger equation for the same billiard, the same potential. Here's a picture of it. This is a schematic picture showing the closed box. That's the real thing. It's just a big slab of brass. And this is kind of an important thing. This is a cross-section through the coupler, the antenna, that brings the waves in and out. So there's a coaxial cable that brings electromagnetic waves in. They then go to this antenna, which is polarized vertically, creating this electric field that obeys the Helmholtz equation, then propagates out the walls of the cavity, and then you get resonant response and so on. So if we take the lid off of this box, you look into it, you see a very thin 8 millimeter deep pocket. You can see there in the space. That defines the billiard region, and that's just a close-up of the antenna, the bottom of the antenna here. Just showing you that the center conductor, the coaxial cable that comes down and acts like an antenna that broadcasts into the box. So we take this box, we hook it up to a thing called a network analyzer, which is a beautiful thing because it measures the scattering matrix. So we've all familiar with scattering matrix. Quantum mechanics is the same exact quantity. It's a complex scattering matrix that measures the transmission, reflection, magnitude, and phase as a function of energy. A beautiful thing. And so we can completely characterize the scattering properties for an open system, which has 2 or more ports, or 1 or more ports, I should say. All right, so we measure over a broad range of frequency up to about 19 gigahertz, where we start to have higher order modes. So we typically have about 750 modes to work with. So lots of good statistics we need for doing our statistical analysis. So let me talk about first closed wave chaotic systems, then I'll talk about open systems, then I'll talk about all the non-universal things that can happen. So first closed systems. So this is a quiz. These are now standing wave eigenfunctions of the same billiard, but under 2 very different circumstances. This is experimental work that was done by an undergraduate in my lab, who's now a professor at the University of Connecticut. Good kid. The 2 eigenfunctions have almost the same energy, you see from these 2 numbers. What we're plotting here is the normalized wave function. So it's the probability density times the area. So it's a number between 0 and infinity. It's the local density of psi squared. These are both normalized eigenfunctions. They're plotted on the same scale, 0 to 18. And the 2 of them differ only in one thing, and that is one of them has a magnetized ferrite. The other one has a demagnetized ferrite. Why did I do that? Because by putting a magnetized ferrite in, I can go between a GOE, the Gaussian orthogonal ensemble, where there's only a single fluctuating random matrix element in the Hamiltonian that describes the wave propagation, versus when I magnetize the ferrite, I go into the Gaussian unitary ensemble, where I have 2 independently fluctuating degrees of freedom on each matrix element. So in one of these cases, time reversal invariance is maintained. In the other one, it's been destroyed. Okay, so the question is, 2 questions. First of all, what's the difference between these eigenfunctions? Right? There's very clear qualitative differences between them. Once we identify the differences, then the question is which one is the time reversal invariant one and which one is the time reversal broken case. Right? So these are two kind of characteristic wave functions. Does anybody want to volunteer some observations about these two eigenfunctions? How do they differ? Jonas.
Well, the upper one seems to have more peaks. The bottom one seems to have fewer larger peaks.
Yeah. So these are more spiky. And if you notice closely, these are kind of rounded off. And you're also noticing that there's a lot more gray area in this eigenfunction. There's a lot more white area in this one. Okay. So those are some key observations. Another thing that's less obvious is the two-point correlation function. If you're sitting on top of one of these peaks, how likely are you to find another peak in a given radius around the first one? This one, as it turns out, has a stronger two-point correlation function than that. So very good observations. Now, given that, which of these two eigenfunctions represents the time reversal invariant system, and which of them represents a time reversal broken system? Do you know anything about weak localization in condensed matter physics? It's manifested in these eigenfunctions. Any thoughts?
I'll guess the top one is the one with the magnifier.
You are correct. Very good. It's very rare that an audience member ever gets this right, so I'm very impressed. Very. I've stumped Nobel Prize winners on numerous occasions with this question. So anyway, that's very good. Absolutely correct. So this is the magnetized ferrite case. This is the broken time reversal invariant. And this is the one where the ferrite is still there, but it's been demagnetized. So it's just all the domains are equal and opposite. And so this one has maintained time reversal invariance. It's quite a nice result. So the way we look at that is just do statistics on the eigenfunctions. We make many measurements of many different eigenfunctions of these two different classes. And then we can find from statistical behavior just what's the likelihood of finding a given value of psi squared. That's all you have to do. Here are the two cases, the crosses and the circles. So in the case of the time reversal invariance system, there's a lot of white space, which is large values, a large abundance of small psi squared, so that's the white space. The gray area is this intermediate regime, where psi squared is on the order of 1, lots of gray stuff. And then those big spikes are these tails out here at very large amplitudes of psi squared. So the beauty is that these fits are not really fits at all. These are the predictions for random matrix theory for the probability of finding a given value of psi squared. There's no parameters associated with the functions. Either pure exponential in the great time reversal invariant, straight line, or this form when you have time reversal invariance. So there is a degree of freedom, which is this number of matrix elements, number of independent degrees of freedom in matrix elements. But once you get that, these are absolute predictions for what goes on. And you can also look at 2-point statistics and things like that. Good agreement with the predictions of random matrix. Okay, so that's just an example of what you see in what I would call closed systems, so closed eigenfunction system. And now the question is, what about scattering? So now we've got this chaotic system, and we've put 2 or more channels which are very strongly coupled to the eigenfunctions of the system. We're looking at transport, say, through or reflection from these kinds of systems, and it's expected as well that there be universal statistical properties. And just to illustrate a few of these, the first is the nuclear scattering. So again, taking a complex heavy nucleus, throwing a neutron at it, and looking at a neutron coming out, looking at the products that can happen to many different kinds of channels of scattering. So this one is a proton into fluorine-35, producing sulfur-32 and an alpha particle in a certain direction. Right? So it's a certain kind of a scattering process involving certain kinds of incident and outgoing scattering channels. This is the differential scattering cross-section as a function of the energy of the proton that came into the nucleus. And you see this wildly fluctuating function of energy, which is not noise. It's a reproducible function. These are things that were measured at Caltech when I was a graduate student. I remember all that stuff. These are called Ericsson fluctuations. So they're well known in nuclear physics. They've been around for many years. Related quantity is conductance measurements through a 2-dimensional electron gas. arsenide or doped gallium arsenide, where electrons can come in, move around in Bunimov exposure, which I've already shown you, and then go out to another channel. And you can measure the conductance associated with this. In this case, it's plotted with resistance versus perpendicular magnetic field. And again, you see these wildly fluctuating variations, which are very large in magnitude compared to the mean. And these are very reproducible. These are not noise. These are fluctuations that are deterministic in nature and reproducible. So these are associated with universal conductance fluctuations. And finally, in the experiment that I've just been showing you, we can also look at scattering matrix elements. And we again see that the scattering matrix elements show these wildly fluctuating variations with energy or frequency in this case. And it turns out all of these phenomena have a common underlying origin. Again, these are not noise, these are reproducible effects. The common underlying origin basically is random matrix theory, once again, that at least for a unitary scattering system, the eigenvalues of the scattering matrix live on the unit circle. They are repelled from each other. They don't interpenetrate, they don't pass each other, they're repelled from each other. And the degree of repulsion is measured by the number of degrees of freedom of the random matrix elements in random matrix theory. So 1, 2, or 4, which basically acts like a temperature. It's a measure of the temperature of this gas of eigenvalues. And just this simple prediction for the probability distribution function for the eigenphases of the scattering matrix alone allows you to basically derive the existence of the Ericsson fluctuations, the universal conductance fluctuations, and all of the physical properties of scattering that we get from our microwave cavities. It's an amazingly simple origin that can explain a vast variety of data. That's the beauty of this. So I won't go through this in any detail, but we learned how to make predictions about the statistics of impedance or scattering matrix. I won't go into this in any detail. But we also learned how to do it when we have non-unitary or subunitary systems. So we pushed the theorists very hard to make that happen. So we defined a new order parameter, a loss parameter, which is basically the width of the resonance divided by the mean spacing. And as you vary that quantity, the statistical properties, universal statistical properties vary continuously. That's been shown theoretically. We've also shown it experimentally. Universal conductance fluctuations basically arise from the same physics. They define a dephasing parameter, decoherence parameter, which we proved experimentally and theoretically is 4 pi times this loss parameter. So we have a direct connection with what the condensed matter folks do. Then I'll show you an example in just a second here of how we're able to uncover universal fluctuations in real data. So again, these are all things that have a common underlying origin. Okay, so I think I'll conclude pretty quickly here by just going through one more example of how we use this whole VGS conjecture, random matrix theory, to learn about the common universal properties of complex systems. But at the same time, we have to fight against the effects of non-universal and system-specific effects that come into play. So let me just illustrate how this works in the context of our experiment. So what we're interested in is some kind of array chaotic cavity. This could be an acoustic resonator, it could be an electromagnetic resonator, it could be a quantum dot, it could be a nucleus. It's connected to the outside world by one channel or one port. And we send waves in, and then of course we're going to look at waves that come out of the system. So it's a typical way that you would examine a complex system. So the incoming wave comes in, goes through what we call a port, which is a way of communicating between the closed system and the outside world. First thing that can happen is that immediately a certain fraction of that wave energy is immediately rejected by the system. It's called the prompt reflection, the prompt response, which is well known in nuclear physics. The same thing happens in electromagnetism. A certain fraction of the energy that never gets into the complex system. There is a small fraction, or some fraction of the energy does get in, and it is subsumed in the chaos, the underlying classical chaos, the wave chaos that exists in the system that transmits signal. But there's another feature. Right, so this is the first non-universal feature. This will depend on the details of the scattering channel and the system that you're going into. This blue part is universal. But there's another non-universal feature, which is the fact that once the energy gets in, sometimes it sees a big flat wall and it just comes bouncing right back out. They're called short orbits. These are seen in nuclei, they're seen in acoustic systems, they're seen in electromagnetic systems. So we learned how to quantify both of these effects very precisely in a very general way that applies to any kind of wave phenomenon. So we've been able to account for the non-ideal coupling and also these short orbits in the system. So we did it in the context of electromagnetism, but it's broad in general. It works for any kind of wave chaotic system. So let me just illustrate this with a few results. First theory, a little bit of experiment. So what we're concerned with, in particular, at least our funding agencies are concerned with, is electromagnetic waves coming in through an enclosure that might be a computer box that's filled with all sorts of sensitive stuff like transistors, clock trees, hard drives, so on and so forth. We treat the ways that energy can get into the system as force, like I illustrated a moment ago for a nucleus. We treat the things that we care about that could be susceptible also to generalized force concept of wave chaotic systems. And we now think about this as a combination of the coupling problem, how does the energy get in and out of various things, and we think about also the universal properties of the system. So the coupling problem is determined by what we call radiation impedance, which captures the non-universal aspects of coupling from the outside channel of the system, and the short orbits. These are deterministic quantities which are very specific to the kind of nucleus or quantum dot or electromagnetic resonator that you're working with. And then secondly, there is the universal underlying fluctuations which are given by the predictions of random matrix theory for a given amount of decoherence or losses. Those are very well established statistical properties. So it's the combination of these two things which actually gives you a complete description of any particular complex system. So when you think about the impedance, which is something that relates to the voltage that appears on port 1 determines the current that appears on all n ports, may or may not be a useful quantity, related to the K matrix from the nuclear scattering theory. But that can be thought of as being a mean part, which is basically characterized by all of the non-universal stuff, and a fluctuating part, which depends only on random matrix theory. Ultimately, it can be written in this form, rather bizarre, but C is a universally fluctuating quantity defined by random matrix theory, and its real and imaginary part of the complex radiation simply dress the universal fluctuations and give you a quantity which has fluctuations, but also has a mean displacement given by some details. So that's the way we think about things in our what's called a random coupling model, which is quite general. It's been very successful. It's made all sorts of successful predictions about electromagnetic systems. I won't go into that in any detail, but let me just illustrate for you finally how it works. Yes.
So, in my prediction, if I say my damn DC electromagnetic radiation,
Yeah.
what's going to happen?
Yeah, that's what we did here. So this is an IEEE journal paper. We actually took a computer box, we irradiated it, and then we made a prediction for what's the probability that we'll see an induced voltage on a particular gizmo that is inside the box. And the dots are the experimental data, and the solid lines are the predictions of our random coupling model. Done. Done. Okay. Yeah. Done. And that's why we get support from various people. So that helps a lot. So let me just finally illustrate how this works experimentally. So I want to take a very simple example of this microwave billiard that I've been talking about. And what we're going to do is do two experiments, and all we're going to do is change one tiny detail of the experiment. And that is the radius of that antenna. Remember, there was this cylindrical antenna coming through the roof of the microwave billiard box, the lid. And we're simply going to change the radius of that antenna, and we're going to do the following. So it's a single port experiment. So we're going to send waves into this port and then look at what gets reflected back. We're then going to create an ensemble of wave chaotic systems by taking complex scattering objects and moving them, twisting them around and moving them to many different locations, about 100 different locations. Make 100 realizations of the system. They all have the same area, but different details, but all the same universal fluctuations. And when you do that measurement, by doing those two measurements, by changing simply the diameter of this wire from 1.27 millimeters to 0.635 millimeters, you get two wildly different probability distribution functions for this particular wave quantity, which is the imaginary part of the cavity, one port cavity. what's very frustrating about this field. If you make one tiny little change to some detail, you get statistics which look entirely different. In one case, all of the reactive impedance values were positive. In the other case, they're essentially all negative. Right? They can't even agree on the sign. And remember, this happened because all we did was change a tiny detail in the antenna geometry that couples the signals in and out of the cavity. And yet, you get this result that there's no agreement at all between these two different solutions. So that's why this is so daunting. It's like nobody would ever say that there's some universal fluctuations being reflected in this data. Clearly not. All right, so what you got to do is now solve for this universally fluctuating quantity in the measured data. So in other words, I have to invert this equation. I just told you is the random coupling model. If I invert it, I now call this thing Z rather than C because it's an experimentally derived quantity. But you can see what I need to do is I need to divide through by the radiation resistance and I need to subtract the radiation reactance from the data. When I do that, random matrix theory, random coupling model says this quantity, this little Z, should be given by random matrix theory, which means it should be exactly the same for both of these two data sets. So when I do that, when I follow the description of taking this raw data, converting it into this normalized little Z quantity, these are the two PDFs that result. Okay? In other words, I strip away the details, the system-specific details, and that allows me to uncover the underlying universal fluctuations which are described by random matrix. Okay? So that's the basic idea. You look at this raw data and you say, there's no way there's anything universal about it, but in fact it's there. You just have to know how to find it. Okay, I'm going to skip this last part and finish. This is fun. I can talk about it informally later. We won a bunch of awards for using wave chaos to make a new kind of technology of wireless power transfer of a large distance. That's done with a group of undergraduates. And anyway, let me just conclude by just showing you some of my colleagues, some head off comments, some of my theory colleagues. John Rogers used to play a big role, but now he's moved to the Naval Research Labs. These are various former postdocs, undergrads, and graduate students, most of whom have gone on to other things now. And we just conclude by saying that classical chaos does play a role in electromagnetism, in quantum mechanics, in many different kinds of wave phenomena, even though it's not obvious. It's there. You have to know how to look for it. But one can find lots of cool stuff. For example, eigenvalues. You'll break all degeneracies if you have a classically chaotic quantum system. You have very strong fluctuations in the eigenfunctions that you look at. And then, of course, the scattering and open properties are also quite interesting. We've also learned how to account for dephasing, decoherence, and loss, and still recover, still see the beautiful underlying behavior as well. So I just wanted to thank you for showing up on a Saturday morning and listening to this stuff. Thank you very much.
Any questions? I have one. The last class we worked on the have you applied for the
Yeah. Yeah, we won the Invention of the Year award this year. University of Maryland, me and a bunch of undergrads. We put in a series of patents for long-range wireless power transfer based on a combination of universal fluctuations in complex environments and time reversal invariance for wave equation. Those are the principles that govern this.
So if we had carbon copy in standard, if you of our undergraduates, how much time, how much money and to be here?
To do this?
Yeah. Carbon copy.
Yeah. It would be minimum of $1 million.
$1 million. So it's really cheaper than looking at the universe. Then we have to do it.
Yeah, this is all paid for by a zero grant.
Yes.
I don't really have pictures of it.
That's okay.
But yeah, it's a pretty expensive thing It's getting cheaper. I mean, you could do it on the cheap for a lot less.
Yeah, because you know, sample much here in the Mali and the Senate, trying to do wireless again of 35,000.
I mean, you can do something.
I know. I'm not
If you want to do a carbon copy, then
yeah, I want to do campus talk. I want to do campus talk. But it's still cheaper.
yeah, but it's got to be.
I know.
Got to be focused on.
Any other questions?
How about
So all the different people wrote. That's the meeting. Start looking at the ground data for the first site. All these things. Even all the you get zeros of statistics. Well, again, these things really only become clear on qualitatively.
Let's thank the speaker again. And let's take a few minutes of